let's just get a simple question out of the way now. So what is become very simple now? When are two coverings isomorphic? Okay, that is to say I have covers, let's call them y, and I have x, and I have p, and I have y prime, and I have p prime, and I want to know whether there is f, which goes like this, and we want it to be invertible, that is f is homeomorphic. Okay, so this can be answered fully, very easily, using what we have seen before. Namely, let's just assume things are non-empty. Okay, so let's pick x0 here, and then we pick y0 here. Okay, and let me say let y0 prime be in p prime inverse of x0. Okay, so I have y0, but I don't want to put it there because that diagram may not commute. Okay, and so what we want is we want for some y1 prime in p prime inverse of x0, we want y0 goes to x. We have x0. Okay, this is the map P, and this is the map P prime. Okay, and this is y prime and y1 prime. So we temporarily fixed this, and again we want to have f here, and this is a homeomorphism. Okay, so this is not a question of asking if the diagram has a solution, because there's another quantifier. This is not fixed. All we know is it's in the fiber. We want to know this. Okay, that's for a very simple reason. The point y0 should go to some point. So if we have a deck transformation f at all, I can take this as by definition f of y0. And conversely, for some particular y1 prime we have a deck transformation, then, oh sorry, I'm using the word deck transformation, that's not correct here. We have a homeomorphism. Then of course we have a homeomorphism from y to y prime, so the diagram commutes if we forget the base points. Okay, but how does this help? Well, this helps in the following way. So let h equals of course p star of pi1 of y0, and h prime is p prime star of pi1 of y0, the y prime and y0 prime. So we chose the base point and had these. Okay, so then there exists y1 prime with the below diagram. That is, there's a homeomorphism. Well, if and only if h prime is conjugate to h. Okay, this is an immediate consequence of the previous observations, because we know that if I took a different base point and we had such an isomorphism, that corresponding group is conjugate to h prime, and h prime and must be equal to h, because we have such an isomorphism. But conversely, given any conjugate subgroup, you can find a corresponding base point, and when you find the corresponding base point, you map the groups become equal. Okay. So this is how we see that we can completely answer. We see covers correspond, well, we don't know whether they exist, and in general that needs hypothesis, but are unique given the fact that given the corresponding groups are conjugate. I mean, they're equal if they're uniquely determined by the conjugacy class of a given subgroup. Also, at this point we should emphasize that if the isomorphism exists with fixed base point or otherwise, it's unique. This is because of uniqueness of map lifting, and that's what we'll use next in understanding symmetries of covers, what are called deck transformations. So what are these deck transformation symmetries of covers? Formally, we just have a cover y to x, and we have p, and we have y, and we have p, and f is a homeomorphism from this to this. Okay, we saw translations or deck transformations of the line covering S1, and you can go back and look at all those pictures of covers of the space which is a wedge of two circles. So they have various numbers of deck transformations. Most of the nice pictures have lots of deck transformations. Okay, so what is this? So this means, so we'll just pick base points. Pick x0 in x and y0 in P inverse of x0. By the way, here throughout I'm assuming connected and locally path connected, hence path connected. There was a blanket assumption, but let me remind you, otherwise these kinds of things are not true. Okay, so now, so f of y belongs to again P inverse of x0. Okay, so and f is determined by f of y. Okay, why is that? That is because if I look at f of y, so then I have y0, this maps to x0. Okay, so this is a pair, and this is y and f of y0, whatever f of y0 is. We have this commutative diagram, and this is a based cover. And so uniqueness tells you that if we have f of y0, okay, so this is a point in P inverse of x0, so it's, if such a map exists, it is unique, and such a map can exist only for points in the fiber. Okay, so further we know that for y, suppose I pick a point y1 in P inverse of x0. Okay, so there exists f deck transformation. Deck transformation is a homeomorphism as above. There exists a deck transformation such that f of y0 is y1 if and only if, well, we know this happens if and only if p star of pi1 of y0 is equal to p star again of pi1 of y1. Okay, this was the group which we called H, and this was the group which we called well, we didn't call it, it was G inverse HG. Okay, where such that G corresponds to the point y1, or rather the subscript, such that y corresponds, I haven't given the map a name, to the coset Hg. Okay, so remember again, so y1 corresponds to the coset Hg. As usual, you take a path from y0 to y1 and push it forward, it gives you a unique coset Hg, or conversely, you're given G, you can lift it. Okay, so this is wonderful. So when is G inverse Hg equal to H? Okay, so G inverse Hg is equal to H, that just has a name. Okay, so that means that, so G inverse Hg equals H if and only if G belongs to the normalizer, sorry, not H itself, the normalizer in G of H. That is the largest subgroup in which H is normal. It's a subgroup of G in which it is normal. It's the largest subgroup of G, which is, by the way, defined as G inverse Hg equals H, G in G. So this is a tautology. Okay, it's the definition of normalizer. But then we can deduce immediately what the deck transformations are. Okay, namely we know points correspond to the cosets. So different elements G, okay, are so given an element G or a coset H times G, we may or may not have a corresponding deck transformation, but different elements that give the same coset give the same deck transformation. Okay, so deck transformations are simply if I look at the normalizer and then I quotient it out by H. Okay, this follows from the definition because the normalizer is, so the nice thing is because this is a normalizer, H is a normal subgroup in the normalizer, and so we can talk about the quotient, which is a group, and this is the group of deck transformations by what we have seen above. Okay, so finally a cover is called Galois if this is transitive on the fibers. We will come back to this when we give the general theory. So we have a nice description of deck transformations. Okay, by the way, this explains why the universal covers we constructed had so much symmetry, because in those cases H is trivial, so the normalizer is bound to be the whole group. and in the other cases it may or may not be the whole group. Okay, so normalizer will be transitive on the fiber exactly when H is a normal subgroup in all of G, in which case the Dex transformations will be G over H, which gives the very nice Galois correspondence. Okay, so looking ahead, we really have almost the whole picture. What we don't have is existence of covers, except where we explicitly constructed them. Okay, so that's what we'll turn to next, and our first step is going to be to give an example where the covers are not normal, and where covers don't exist. And then there are some covers always, space covers itself, but you don't have enough covers, you don't have in particular a universal cover. And then with appropriate hypothesis, we will construct covers, and that hypothesis is sharp. Okay, so but before turning to that, let's just leave with a definition. Now, definition is what is called a Galois cover. It's sometimes called a normal cover or a regular cover, but I'd prefer to use the word Galois simply because covering already has more than one meaning in topology, and in those other meanings, if you say normal cover, you don't know which meaning of cover you're using in the first place, while Galois is used only in this context. Okay, so this is just like a Galois group, where if you have enough transitive, so where subgroups of the Galois group correspond to field extensions. Okay, so covering map is said to be Galois if Deck transformations act transitively on the fiber, and that means that given any y1, there's a Deck transformation taking y1 to y0, and that is simply equivalent to the group corresponding to this being normal in G. Okay, so we have a nice fully algebraic picture. We have a group, a subgroup corresponds to given a cover. We have a group which is the fundamental group. Given a cover, we have a subgroup corresponding to that, and we have symmetries of the cover which correspond to the normalizer of the subgroup, quotiented by the group itself. The fiber corresponds to the cosets, and so in the normalizer the group is normal, the quotient is the Deck transformations, and if the group is normal, then the cover is fully symmetric. This is the Galois theory except for existence.